Okay, then I will start. So welcome everybody. The presentation is about efficient model-based control methods for urban and freeway traffic networks. And this is actually joint work with a number of past PhD students and postdocs, including Shulin, Solomon Zegeye, Lakshmi Bhaskar, Anahita Jamshidnejad, and Rudy Negenborg. And this is the overview of the presentation. So first I will tell a little bit more about the model-based control method called model predictive control and how it can be applied for traffic networks. Then I will highlight the main challenges if we want to apply MPC for traffic networks, in particular for large-scale traffic networks. And then I will gradually consider several possible solutions to deal with the complexity issues. This includes looking at traffic models. And then we will also look at different forms of MPC, variants of MPC, that make the problem more tractable. And these include parameterized MPC, distributed MPC, and multi-level MPC. And at the end of the lecture, I will provide a summary. And I expect that there will be a break somewhere in between the third and the fourth topic. Also, if you have questions during the presentation, please feel free to interrupt me. And I will also, during the break, there will also be an opportunity for questions, and of course, after the presentation. So let's first sketch a bit traffic management, what it means. In this presentation, I will mainly look at conventional control measures. So we consider vehicles, human-driven vehicles. And the idea is to make use of the roadside intelligence to get the best possible behavior of the traffic network. So that means that we assume a traffic control center and also infrastructure. The control measures can include traffic signals in urban contexts, but also variable speed limits. That's what you see here on the right. So a portal above the highway where speeds are displayed. And later on in the presentation, we will give an illustration how these speeds can actually be used to reduce congestion. We also consider ramp metering. So here you see an example of ramp metering. At the back, there is the main highway. At the front, there is an on-ramp. And here we have, again, two traffic signals. And they will actually allow vehicles to pass one by one and to enter the highway. With ramp metering, you can make sure that the density, so the number of vehicles on the main highway, stays below a critical density. So that's also a way to control traffic. Additional ways to control traffic are lane closures. So that's when you cross out one of the lanes. Often during rush hour, the emergency lane might also be opened, and that's called shoulder lane opening. And finally, in some places, suppose that you have 3 lanes of a highway. It could be that maybe in the morning, 2 lanes are used to go into the city. And in the evening, only 1 lane is used to go into the city and 2 out of the city. So tidal flow means that the direction of one of the lanes of the highway may change depending on whether it's morning or evening rush hour. In addition, in this presentation, we're also going to include so-called soft control measures. For example, dynamic route information. That's what you see here at the bottom right. And so we have a route information panel that would indicate that if you want to go to the airport of Schiphol, that to the left, there is a traffic jam of 3 kilometers, and to the right, there is a traffic jam of 2 kilometers. And mostly these information panels are used to provide real-time information, but in exceptional cases, you may also want to use them to control, to steer traffic a bit in the right direction. And we often call it anticipate traffic control. So the idea is that you may want to kind of deviate a bit from the real-time conditions here, so to try to steer the vehicles in a particular direction. Of course, you have to make sure that if you change the values a bit from the real values, that you actually make sure that they are close to reality, because otherwise people will not trust the messages next time they pass. So that's called a soft control measure. So you can steer in a soft way the the vehicles, the drivers, but you have to make sure you don't exaggerate. Then this concludes the control measures. So we have hard control measures and soft control measures. And for the performance criteria, we can look, of course, at the total time spent. So that's the total travel time of all the vehicles. But currently, we're also looking at so-called green mobility. So we take sustainability performance measures into account. And that means that we will also look at fuel consumption, emissions, noise, and so on. And in practice, we often use a weighted sum. So we assign a certain weight to each of the control of the performance criteria. And together, we add them. And then together, they form the overall control measure. So that's the setting for traffic management. And what we are going to do in today's lecture is to see how we can do traffic management using a model-based control approach. And the control approach that we are going to use is called Model Predictive Control, or MPC for short. And these are the features in a nutshell. So it's actually originated in the processing industry about, I think, 60, 70 years ago. So that is very popular. And it's popular because it's model-based and easy to tune. We will see later on that there are only 3 essential parameters to be tuned. In addition, it allows to deal with systems with multiple inputs and multiple outputs. And actually, the most important feature is that it allows to include constraints, both on the inputs of your system, the states of the system, and the outputs. And in practice, but I will explain the next 2 items in the next slide. So we have a moving horizon approach, and we can use either offline or online optimization. To illustrate the last 2 items, I will first explain how MPC works. So on the right, you see how MPC works. We have a system that we want to control. This can be a traffic network or any other system. And the idea is that we first make measurements to determine the current state of the system. And then we go to our controller. The controller has a built-in model of the system that is used to predict how the system will react to certain control inputs. And then we have an optimizer. So we have here a loop where the MPC controller proposes some control actions. The model is used to see what is the effect, both regarding the objective, the performance, and the constraints. And this is then fed to an optimization module. And then in an iterative procedure, the optimal control actions will be found that will minimize the objective over a certain horizon, while also taking the constraints into account. And these control inputs are then fed back to the system. And then after a while, we repeat the whole procedure. So we measure the state of the system and we optimize. So the objective in a traffic context would be the total time spent or the emissions. The constraints could be, for example, constraints on queue lengths, constraints on densities, and so on. And we consider receding horizons. So we are actually going to look n steps ahead. So we assume here that we have a discretized control setting. So we have that, for example, at every minute, we will consider the state of the system and also how the dynamics of the system evolve. And we look n minutes into the future. And the idea is that for those n minutes, we determine the optimal control inputs. So that's done via an optimization problem where U defines or represents the control actions. So the settings for the traffic signals in an urban context, or the values for the speed limits or the ramp metering rates in a freeway context. And of course, we also take the constraints into account. Okay, so receding horizon means that we are at a certain time step. We look n minutes into the future. For example, in a freeway context, this could be that we look like 30 minutes into the future. So we determine the control actions for the next 30 minutes, but we only apply the control inputs for the next minute. And then after 1 minute, we measure the state of the system again, and we again optimize for the next 30 minutes. So we always have a horizon of 30 minutes that shifts, and that's called receding horizon. Most of the time, the optimization will be done online, But there also exist settings where you can automatically translate the state, the objective, and the constraints into the control inputs. In a linear context, this can be done in a piecewise affine way. And in some other context, you can kind of train, for example, a neural network to directly map the state, the objective, and the constraints to the control inputs. But in today's lecture, we are mostly going to use online optimization. So we measure the state and we do an online optimization of the control inputs. What is the main problem in practice is that the optimization problem that you want to solve is both nonlinear and non-convex in general. And that means, essentially speaking, that if your system becomes more larger, more complex, that the computation time will increase exponentially. And so generally speaking, this nonlinear, non-convex optimization problem is characterized as a so-called NP-hard problem. So in general, we have a huge computation time, in general, also for large-scale systems. However, in practice, we have only at most 1 minute to compute the solution of the problem. And that means that for large-scale systems, we cannot just straightforwardly apply this approach, because then if we only have 1 minute to optimize, then we will not get optimal solutions at all. So we need solutions. And some of the solutions that we are going to discuss in today's lecture are listed here. The first one is to be aware that there is a trade-off between accuracy, so how accurate you want to be with your model, and your computational complexity. So in general, if you have a very accurate model, you will need a long CPU time. If you take a more approximate model, then you will need a lower CPU time, but this will go at the cost of reduced performance because you're deviating much more from reality. So that's the first solution that we are going to consider. The second solution is not to optimize all the inputs, but to capture the inputs with the so-called controller that has a parameter, and to optimize the parameter instead. Next, we will talk about distributed control and hierarchical control. And actually, these two topics will also be considered in some of the other presentations that will be given later today. We can also look at using the right optimization approach. So sometimes you can use a gradient-based approach. And if you can compute a gradient analytically instead of numerically, that can create a huge speed up. In addition to distributed control, you can also go for distributed or parallel optimization, or you can simplify your original optimization problem by another optimization problem. Actually, this will also be discussed later on at the very end of the lecture, where we are going to approximate a nonlinear, non-convex optimization problem by a mixed integer linear programming problem. And finally, and this is important not only for traffic networks, but also for other type of infrastructure networks, is to include application-specific knowledge. So let's start with the first solution, namely the traffic model. And in general, if you look at traffic networks, we have two extreme types of models. The first one is called microscopic models, and there you're actually going to model or to track the behavior of individual vehicles. The other type of model, so at the other end of the spectrum, we have macroscopic models, and there you're going to work with aggregated variables. So you're going to divide your traffic network in a number of stretches, for example, stretches of maybe 10 kilometers. And for each of those stretches, you're going to work with, for example, average density, average speed, and so on. So let's first look at the microscopic traffic flow models. So they consider individual vehicles, and they describe some of the behaviors that cars may have. And so how does a car follow its predecessor? And then we mainly look at the distance. So the distance keeping between a car and the predecessor. There are also models that describe when we are going to change lanes. And finally, when we are going to overtake another car. Typically, these models also include different driver classes. So that means that we may have drivers that are like patient or drivers that are aggressive, and they may have different parameter settings regarding the behavior for car following, lane changing, and overtaking. If you look at these models, especially for large networks, then we see that since they describe individual vehicles and really track the behavior of each individual vehicle in detail, that they will be very time-consuming for large-scale networks because we have to model and update the behavior of each individual vehicle. That also means that they are less suited as a prediction model for MPC. And then I will go back to the slide for MPC. And the reason is that in MPC, we have here an optimization loop where we use the model in the optimization, in the iterative optimization procedure. So in practice, we are going to run the model a lot of times to be able to find the optimal solution. And so typically for a nonlinear optimization problem, you may need to have like 100 or even thousands iteration in one prediction horizon, so within 1 minute. And that means that you need to run your model very, very often within a limited time span. And if we then have a very complex model, such as a microscopic model, that means that it's less suited to be used as a prediction model for MPC, so as a model inside the optimization loop. However, if we look at simulation or validation, then these models are, of course, better suited because they model in a much more accurate way how the real traffic system behaves. Another way to consider models is to work with aggregated variables. And so I indicated that you might consider links, and the links can be divided in segments. And in every segment, you may look, for example, at the average speed, the average density or flow, or if you look at an urban network, at the number of vehicles or at the queue lengths. And we will consider two types of models. So for urban models in the literature, we have store and forward models, cell transmission models. And in today's lecture, I will briefly tell a little bit more about the so-called S model. And for freeways, we also have several macroscopic traffic flow models. A well-known one is the Lighthill-Witham-Richards model. And in today's lecture, I'm going to focus on the MetaNet model. The MetaNet model will also be considered in more detail in the lecture of Professor Papageorgiou later this week. And in general, we have a trade-off between computation speed and accuracy. So typically, the macroscopic models, they will be less accurate because they work with aggregated variables. So they're less accurate, but because you don't model every individual vehicle anymore, they will also typically be much faster to run than a microscopic model. So this means that they are well suited as a prediction model for MPC, but less suited as a simulation or validation model. We are going to use the S model for urban networks and the MetaNet model as a prediction model for MPC in this presentation. But it's important to note that the approach, so the model-based approach that we present, is generic. And that means that you can also use all these other models if you want. So first, the S model. So the S model is a model for urban networks, and it's discrete in time. And in this particular model, we are going to update the variables every cycle. So a cycle is a sequence of, let's say, settings of red, green for your traffic signal, and it's typically cyclic, so it's periodic. And during one cycle, the traffic signal will, let's say, evolve, so the cars will move. And we just look what happens at the beginning of the cycle and what is happening at the end of the cycle and how these values are related. We also assume that there's one cycle time per intersection, and the states are twofold. We have on the one hand the number of vehicles in each link, and also the queue lengths at the end of the links. And at a high level, we then have the following situation. So we have a link, and there are entering flows. So at this intersection, we have three, let's say, feeding links, and they all send vehicles to the link under consideration. the vehicles enter, and after a while they arrive at the queues. And we assume here in this model that there are queues for every outgoing link. And so we have here 3 outgoing links for our link UD. And that means that we have 3 queues. And what we're now going to see is how do the variables, so the number of vehicles in the link and the queues relate. And these are typically based on conservation laws. So for the number of vehicles in the link, we say that the number of vehicles at the next time step is equal to the current number of vehicles plus the inflow minus the outflow. Then we also have to relate the number of vehicles that enter the link with the number of vehicles that arrive at the queues. So alpha enter is the number of the flow of vehicles entering the link, and alpha arrive is how they arrive at the tail of the queue. And how is this described? We look at the distance that the vehicles need to travel. So they need to travel from the beginning of the link to the tail of the queue. So that's characterized by the so-called storage space length. So this length corresponds to the storage space, and we just divide it by the speed of the vehicles. And then we know how much time the vehicles need to go from the beginning of the link to the queues. Since we are working with a discrete model, we need to round this to an integer. That's where the floor comes from. And of course, we take the average, or we take a weighted average between the vehicles entering at k minus tau, where tau is the lower, let's say, integer of the actual travel time, and the next value. So this is then the ceiling of the travel time. And depending whether we are closer to the floor or to the seal, we take a larger part of the flow into account. That's where this remainder of the division between the travel distance and the speed is taken into account. And in that way, we can relate a number of arriving vehicles to the number of entering vehicles. Then again, we can update the queue lengths. So the new queue length is the old queue length plus the number of vehicles that arrive in the queue minus the number of vehicles that leave. And to determine how many vehicles leave the link, we have 3 factors. First of all, we have to take into account how many vehicles can be processed by the intersection. So every intersection, due to its layout, its geometry, has a maximum number of vehicles that it can process. Moreover, we can only have vehicles leaving the intersection if they've arrived first. So we look at the number of vehicles arriving. And finally, we also look at whether the downstream links are blocked or not. So we take into account how many vehicles can the downstream link accept. And that will then describe how many vehicles can leave the intersection. So what is the kind of summary for the S model? So we have 1 cycle time per intersection and also a separate counter per intersection. In general, we also have to take into account that the cycle times may differ per intersection, and that might also be an offset. But there are some equations that describe how you can interconnect these 2 variables. So we have an interface between the 2 intersections. In general, if we want then to apply MPC, we get a model that has a nonlinearity. And there are actually 2 nonlinearities. One is actually caused by these integer approximations of the delays. And the second is caused by the fact that we have the min of 3 quantities. So these are 2 nonlinear, non-convex, let's say, factors. And in general, although the problem is nonlinear and non-convex, we can approximate it using mixed integer linear programming. For the S model, I will not go into detail, but later on in the presentation, we will see how this transformation can be done for another problem. And I just want to illustrate what this means. So this side I'm going to skip. This is the interfacing between 2 intersections. And we are going to consider a very simple setup. So we have an intersection, a grid with 4 intersections. The simulation model is actually also macroscopic, but with a simulation time of 1 second. So it's much more accurate than the S model. And we consider cycle times of 2 minutes or 1 minute. And the prediction horizon is then 10 cycles, and we simulate for an hour. And we are going to consider several optimization methods. The first one is a standard method for nonlinear, non-convex optimization problems called SQP, sequential quadratic programming. And we do it with a multi-start approach. So typically, if you have a nonlinear, non-convex optimization problem, then you need a multi-start approach to find a good approximation of the optimum. So we use 5 initial points. And we also use pattern search, that's a gradient-free solver. And finally, we use the MLP solver, and there we use CPLEX, which is a well-known solver. And then you see here the results. So we have SQP and pattern search, which are true nonlinear solvers. And then we have the MLP solver and also the S star, which is a further approximation of the S model. And then you see here the total time spent, and we see that in this particular case, the nonlinear solvers actually, because they cannot really solve the problem to optimality in the given time span, that their performance is actually worse than the MLP solvers. If you then look at the CPU time, then you clearly see the huge difference that you have between solving a fully nonlinear, non-convex optimization problem and using an approximation. And actually, in this particular case, the approximations even yield a better solution than the nonlinear solvers because we could not take enough starting points for the nonlinear solvers. So that's the first message. On the one hand, try to go for macroscopic models. And if you can then further simplify your model, that's also highly recommended. So this was about the S model, which we use for urban freeways, for urban networks. We also will briefly discuss the MetaNet traffic flow model, which is used for freeways and also for major urban corridors. So this model was developed by Papageorgiou and Mesmer. Actually, Professor Papageorgiou will give a presentation later this week, and then he will also come back in more detail to the MetaNet model. And it has been extended in various ways. And the idea is that we present a network by a graph. So every highway is divided in stretches, and the idea is that every stretch has uniform characteristics. That means that if we have a change in the dynamics or in the characteristics of the highway, for example, if there is additional lanes or if we have an on-ramp or an off-ramp, we start with a new link. And then the changes in geometry, they correspond to nodes of the graph. Next, we are going to divide every link into segments of a certain length. And typically, we take a length of, let's say, 1 kilometer. And that's what you see here. So we have a freeway link, and it's divided in n segments. And for every segment, we are now going to consider 3 characteristic variables, namely the density, which we will represent by rho. We also look at the outflow of the segment, which we will present by Q. And we also look at the speed of the vehicles in the segment. And let us now discuss the relations between those variables. First of all, for the density, we have again a conservation law. And so we look at the outflow that is here Qi. We look at the inflow from the preceding element. We also modify them with the time, and we divide them by the length and the number of lanes to go to a density. And then we add this to the current density. By the way, the density is the number of vehicles per unit length. So it's typically expressed in vehicles per kilometer. And with the law that I've presented here, we can then update the density of the vehicles in a segment. The flow is actually not a real state variable, but it's related directly to the density and the speed and the number of lanes. So this is an algebraic relation. And finally, we also have an equation to update the speed, and that consists of the previous speed and 3 update terms. So let us discuss the updates. So the first one expresses that for every density, we have a desired speed, a desired steady state speed. I will present this curve in more detail on one of the next slides. And the idea is that if the current speed in the segment is different from the desired speed, we have a tendency to evolve towards the desired speed. So that's why we update the current speed with the difference between the desired speed and the actual speed. In addition, we also have a convection term. So if the vehicles of the preceding section have a higher speed, that speed will also propagate to the current section. So that's why I have this term here that looks at the difference between the speed in the preceding section and a segment and the speed in the current segment. And finally, we have an anticipation term that expresses that if the density in the downstream, so in the next segment, is higher than the density in the current segment, then vehicles see that there's a traffic jam ahead and they will decrease their speed. That's why you have a minus sign here. And with these three phenomena, we then update the speed in the current section. So let's now look at the so-called desired speed. So what you see here is a plot that relates the desired speed with the density or also the flow with the density. And let's focus on the right plot now. So here we have the density, so the number of vehicles per kilometer on the highway, and we look at the speed. There's a question? Okay. Okay, then I will go ahead. So if the number of vehicles on the highway is very low, you would typically go to the free flow speed. So that's indicated here with VF. So if the number of vehicles is low, you have a high speed, but as more and more vehicles enter the highway and the density increases, then at one moment you will get a traffic jam. So the speed goes to zero. And this exponential expression is one way to describe that behavior. In general, these relations between density and desired speed or density and flow are called fundamental diagrams, and they might also occur later on in the next presentations by the other speakers again. Okay, so we also want to express the effect of speed limits. And suppose that we have a speed limit in certain section. Of course, we still have the desired speed, but if the speed limit is lower than the desired speed, we will take this into account by considering the minimum. In addition, we will also take into account that not all the vehicles might stick to the speed limit. So we have a so-called non-compliance factor. And what we see in practice, if there is like monitoring, if there are traffic cameras or if the police is actively or regularly monitoring a certain stretch of highway, then we see that the alpha is zero or even sometimes even negative. So then people really stick to the speed limit. In other instances, we will see a deviation between the speed limit and the actual speed, and it might be higher even than the speed limit if there's no monitoring. And with this description, we can even take this non-compliance into account in our prediction model. In the literature, and maybe also in Professor Papageorgiou's presentation, there is also some laws for how to describe origins, or if you want to model the effect of the downstream density, depending on whether it's higher or lower. And so if it's lower, there is no traffic jam ahead. If it's higher, there is a traffic jam ahead, and people may react in a different way to both situations. But for this, we refer to the literature. Let's now not only focus on flow, but also on emissions. So I'm now going to present one of the possible models to describe the emissions of traffic. And for this, we use the so-called VT micro model, which was developed by Ahn and his co-workers. In essence, there you describe the emissions, for example, CO, NOx, HC, or even the fuel consumption as a function of the speed and the acceleration. And here you see for an individual car what the emissions would be as a function of the speed. So typically at lower speeds, we have high emissions. They go down as the speed increases, but if the speed then increases further, the emissions go up again. And we can express the emissions in gram per kilometer, and we typically always have this type of curve that at low speeds we have higher emissions, the emissions go down, and then they go up again. And the same also holds for the fuel consumption or the CO2 emission, which is almost proportional to the fuel consumption. So very high in the beginning, and then they go down, and for higher speeds, they will go up again. In addition, we also have an effect of the acceleration. And so if you have a high acceleration or a high deceleration, if you have a high acceleration, then typically your fuel consumption will be much higher. Of course, if you're decelerating, if you're pressing the brake, your fuel consumption will be lower. In this model, this is actually a microscopic model. So it describes the behavior for individual cars. If we want to predict how traffic networks evolve, we will need to modify it to a macroscopic model. And that's then done using the so-called VT macro model. And I'm going to explain it for MetaNet. In MetaNet, you may recall that we already had an update equation for the speed, but we did not have the acceleration yet. And that means that we need a way to extract accelerations from MetaNet. And to this aim, we actually consider three types of classes of vehicles. So we have in green the vehicles that move from one segment to another. So here from segment I-1 to I. And likewise, we will then have vehicles moving from segment I to segment I+1 if we go from one time step to the next. But there will also be vehicles that stay in the link. If we consider the vehicles that move from one segment to the other, then the number of vehicles is described by the outflow of the previous segment, and the acceleration would then be the difference between the speed in the new segment and the speed in the old segment. So that's how we can capture the number of vehicles moving from the previous segment to the current segment and their acceleration. We also need to describe the vehicles that stay in the segment. And actually there we look at the number of vehicles in the segment, and we subtract the number of vehicles that go out of the segment. And so this here is the total number of vehicles in the segment, and we subtract the pink part. So they are discarded. And then the acceleration of the vehicles that stay in the network in the link, is just the difference between the new speed, so the speed at k+1 in the ith segment, minus the speed at k in the current segment. So in that way, we can connect or derive accelerations that we can then use in MetaNet. And then we just add the emissions for the moving cars and for the cars that stay, and we multiply them with the number of cars. And in that way, we can translate the microscopic emissions into the emissions at the macroscopic, at the segment level. And finally, to illustrate how we can then now use MPC with those macroscopic models, I will explain the issue of shock waves in traffic flows. So typically, if you look at congestion, in some cases, you might actually see that the congestion is moving, is rippling through an entire highway. And to illustrate this, I will show my web browser and show a small movie. So what you see here is a map of the Netherlands. And we have big cities like Rotterdam, Amsterdam, Utrecht. And the white lines, they represent highways. The red spots represent traffic jams. And this is an image from the website of the Automobile Association. And they would typically describe the current situation on the highway. And what we have now done is we have actually monitored several of these images and put them in a sequence. And then you will see the traffic jams move. So you will see some of the red spot move. And it's important to know that in the Netherlands, the traffic drives on the right. So now I'm going to start the animation. Magnify it a bit. And for example, here you see some of the traffic jams and they're moving backwards. So on this part of the highway, the traffic is driving from here to here, but you will see that the red spots move backwards. So I will start again. And so we see in several places that the congestion moves backward. And this is called a shock wave. So let's now go back to the presentation. Typically, they move ahead or upstream with a speed of about 15 kilometers per hour. What is the disadvantage is they will cause extra travel time. And since we have a kind of a shock wave, they will also could lead to unsafe situations. And the idea to deal with them is that we're going to use these variable speed limits. So the idea is that we try to slow down the traffic ahead of the shock wave such that we can reduce the inflow of the congested area, and that actually by the time the vehicles with a reduced speed arrive at the congestion, we have dissolved it. And for this, we will use variable speed limits. That also means that we cannot just apply a speed limit in one place. We really need to coordinate various speed limits and also anticipate what is going to happen into the future. And that means that model predictive control is actually excellently suited to address this problem. And the setup or the case study that we're going to consider is a straight highway of 12 kilometers. So we consider segments of 1 kilometer, 12 segments in total. And a shock wave will enter the highway from the right. And we will have the first 5 segments uncontrolled, then segment 6 to 11 controlled with speed limits, and again, the last segment uncontrolled. And we have some constraints on our speed limits. And I will illustrate what is happening again using some animations. So let's first look at the uncontrolled case. So on the horizontal axis, you see here each of the links. And at the top, you see the speed. And at the bottom, the density. So the density was the number of vehicles per kilometer. And in the highway, so the traffic is driving from the left to the right. And we get a shock wave entering the highway at time 1, at 1 minute. So you will see a combination of a low speed and a high density. So that's a traffic jam. And the traffic jam actually moves in the opposite direction of the vehicles. The vehicles move from the left to the right. The shock wave moves from the right to the left. And if you don't do any control action, then you will see that the congestion moves through the entire link. This will cause delays, and because you get reduced outflow of the region that is congested, and it may cause unsafe situations. So this is the uncontrolled situation. In the next animation, I will show you the controlled situation. So what we have here is in red, we indicate speed limits. So we had speed limits in segment 6 to 11. So that's indicated by the red bars here. At the top, you again see the speed, and at the bottom, the density. At time instant 1, the traffic jam or the congestion will enter. So in segment 12, you will see low speed and high density. But then you will see that the speed limits will kick in. So let's again go through a cycle. So here is the congestion, and here the MPC controller will reduce the speed. And in that way, it will actually create a so-called negative shock wave that will compensate for the shock wave that was entering from the right. And we now see that in contrast to the no control case, the shock wave will no longer propagate through the entire highway, but we will keep on a high speed and a low density here. So we have actually prevented the congestion. It's maybe also good to notice that here there is a difference between the speed limit and the actual speed. So the actual speed is here a bit higher than the speed limit, and that expresses the non-compliance. So some of the drivers will not stick to the speed limit, and we can take that into account in our prediction model if we know the value of the non-compliance. Okay, so then we go back to the slides. So here you see again the same plots that were in the animation, but just as static plots. And the main idea is that if you have no control, the shock wave will go through the entire highway. And if you have control, you're able to kind of extinguish the shock wave and let it disappear. Okay, so I will propose to take a break here and maybe already open the floor for questions if there are already questions on the first part of the presentation.
Yes, Professor Bart, there is a question in the chat.
Maybe questions can either be asked by unmuting your phone. That's maybe the easiest because I cannot see the chat window currently.
Yes, I can ask the question.
Yes, please.
It was about the emissions. And
yeah.
Could you explain why they are higher at lower speeds? That seems counterintuitive to me. Is this statistical? So does it include that you have more gear shifts and more acceleration at lower speeds?
Yeah, it's a combination of, let's say, the behavior of the motor. So this is typically a model that it was developed about 20 years ago. So of course, in more modern cars, these curves for low speed might again be a bit lower, but it's really the behavior of the engines. And it's related to the optimal, let's say, number of rotations per minute. And these are based on experimental data. So they were really like based on actual measurements.
Okay, thank you. And then I would have.
And it's also important maybe to notice that here we express the emissions per kilometer traveled. Yeah. So that's, of course, if you have a low speed, you need more time to cover a certain distance. And so that's also explains why for low speeds you need more time, and then you will in the end emit more to cover a certain distance.
Yes, thank you. And then I would have a second question,
yes.
And that is about the compliance factor for the speed limit. How can you estimate this, and how sensitive is the solution to this number?
Yeah, so the first question on how to estimate the compliance factor is just based on historical data. So you measure the speed limits, and you also check how the vehicles react in a certain stretch to it. And in that way, based on historical data, you can make an estimate of the value of the non-compliance. Then the second question on how sensitive this is. In general, actually, if we look at MPC, let's just show the picture, because the question can be generalized, and it's not only regarding the compliance factor, how much would an error in the compliance factor affect the performance of your system, but in general, how much would a model error affect the performance? And then we would typically see that we have actually a kind of feedback mechanism in this loop. And so we measure the state of the system, we optimize, and then we make a certain prediction about the future, and then we apply the control inputs to our system. But after 1 minute, for example, we again measure the state of the system, and that we get a kind of a correction. If there is a mismatch between the model and the system, by this feedback mechanism, we can already compensate for those errors. And we have done some experiments, and also other authors have done experiments. And typically, if you have model errors of up to 5 to 10%, you could still get a good overall performance due to this feedback mechanism. Does that answer your question?
Yes, thank you.
Okay, thank you. Are there any additional questions?
May I also have a question?
Yes, please.
So would you please comment on the effect of this controller on average travel time of people who are passing through this network? So if applying the controller and having different maximum speeds would reduce or increase the average travel time for people who are passing through the links.
Yeah, so then again, I would like to go to for example, this slide here. So here you see that if there's no control, then actually every car traveling to the network will have to pass through a traffic jam. And typically, if you pass through a traffic jam, so the outflow of a traffic jam will typically be characterized by the fact that people have low speeds and that the distance between the vehicles is also large, and because they exit from a traffic jam. And that means that we have a so-called decreased capacity. So the number of vehicles that we can process at the end of the traffic of the congested zone, the number of vehicles per hour that we can process will be lower because of a combination of low speed and a high inter-vehicle distance. In case there is control, we don't have that shockwave anymore. So that means that the vehicles can still move on. And of course, this will always then give, in the end, a better or lower travel time. Of course, there are two things to take into account. First of all, it really depends on how long the traffic jam is to see how much your total travel time will decrease. In experiments we have done, we can get decreases of up to 20 to 30% in the total travel time. The second aspect is, of course, that our controller takes the travel time into account, but it takes the total travel time into account. So it could be that for some individual vehicles, actually the control may create a slowdown. But in this presentation, we mostly look at the optimum from the network point of view. So the global optimum for all traffic users together. And especially in a network context where we have different routes, it might be that due to the control, some of the vehicles get a somewhat longer travel time. But if you look at the average travel time for all drivers together, that will typically go down. Does that answer your question?
Yes, perfectly. Thank you.
Okay. Are there other questions?
Yes, I have one question.
Yes, please.
In this presentation, you're describing about the model predictive control. Yeah. So are there other, or is it possible to have formulations where you could implement, let's say, a Lyapunov or a sliding mode control? Yeah. And what would be the comparison? Would MPC do better or Lyapunov do better? Or?
Yeah, so there are indeed some people that use Lyapunov-based approaches, but there the main issue is the model. And so of course, for linear models, it's easy to derive Lyapunov-based control approaches. However, in traffic models, we typically have the issue, and I maybe can illustrate it using the S model. And so in the S model, we typically have that there is a nonlinear term. And the same actually also holds for the MetaNet model. And there we had this desired speed. So this update equation, and you see here already a nonlinear term. Here you see a nonlinear term. Yes, and the same also holds for this. So typically you would be dealing with nonlinear models, and that makes Lyapunov function approaches more difficult. The second issue is that Lyapunov approaches are often used to go for stability. So you want to reduce a certain error state to zero. And what some authors do is they kind of, on this fundamental curve, they want to stay a little bit to the left of the breakdown. Yeah? So here, if you look at the density versus the flow, typically at the low density, the flow would increase. It means that more and more vehicles can enter the highway. But at some moment, this levels off. And if there are too many vehicles on the highway, get a breakdown. So you could say if you can stay a bit to the left of the critical point, you have an optimal point. But the problem is that if you're actually in this regime, you're actually being forced to a regime with actually a lower speed, because the optimal point here would be around here, about 80 kilometers per hour. So if you try to reduce an error with respect to a desired state to 0, you would actually penalize the system in the region without congestion. And that makes it a bit more difficult to apply Lyapunov methods to a traffic setting, but it has been done by some authors. In addition, yes, please.
Yeah, no, I understand the point.
Yeah.
Yes.
And of course, the control approach that we present here is not the only one for traffic. And there are many other traffic controllers. Some of them are rule-based. We have fuzzy controllers. We have also controllers that are based on heuristics and that combine, for example, in an urban traffic context, they will look at the density, the number of the queue lengths in the surrounding intersections, and based on that decide which intersection to give green and for how long. And so there are actually in the literature a lot of different control strategies for traffic networks. The main reason why in our research we are using MPC is that we can actually not only use it for traffic networks, but also for other types of networks. At the very end of the slide, I will also kind of relate to water networks, smart grids, and so on. And that's then the advantage that the methods that we discuss, especially in the second part of the presentation, would not only apply to traffic networks, but to other types of infrastructure networks as well.
Okay.
Does that answer your question?
Yes. Thank you.
Okay. Any other questions? Okay, then I would like to ask the organizers, is it typically to have now an actual break, or is it
I think it's fine. We can start. We can continue if it follows your schedule.
Okay, so then we will go back to the presentation. And we will now move, if we go back to the overview. And so we have been talking about the aim for MPC and about traffic models. And we will now look at ways to approximate or to speed up solving the optimization problem, not by looking at the model, but looking at the control approach. And the first approach that we take is so-called parameterized MPC. So in conventional MPC, you would optimize the control inputs, but in parameterized MPC, you're going to make a relation between the state of the system and the control inputs using a parameter theta. And the idea is that we are now going to optimize theta instead of u. That means that in general, we have less variables because theta would be, the number of components in theta would be less than the components in u. So we get faster computation. Of course, it will be less rich because we cannot always capture all the optimal control inputs in that way. So in the previous, we did this. I will go more detail in a minute on how this works. Typically, you will get a huge increase in the speed, so typically 80% faster, with a performance that is comparable to the classical conventional MPC. So how does it work? We now have a setting that is as follows. So we have our system. Again, we still measure the state and we feed it back to a control law. The control law will be used to compute the control inputs. And now we're going to update the settings of the control law using MPC. So again, we have our optimizer module, we have the model, and we have a copy of the control law. And then we use the optimizer to determine the optimal value of the parameters. And this is then be fed back to the system. In general, it's important to note that we can now kind of have a distinction between the optimization, the speed of the optimization, and the speed of the control law. For example, we can now kind of update the control law every 10 seconds, while we still only update the parameters every minute. And so in that way, we can have different time steps inside the first control loop and the optimization loop. In general, if the number of parameters is less than the number of components of U, we will get a significant speed up. So here you typically would see a situation where we are updating the parameter only every 2 time steps. And then we see that we can still have a good variation in the control input, because the control input depends on the state of the system, which is updated every time step, and the parameter. So even although we keep the parameter constant, we can still get a variation in our control inputs because of the controller. In general, you can go to more complex schemes that you, for example, say, okay, I will first update 2 parameters and then keep it constant, or I keep the parameter constant for the whole horizon. In that way, you can still further reduce the complexity, the number of variables. So let's look at some examples. If we look at the freeway context, then we can, for example, say our speed limit is determined by the free flow speed in the segment. And then we take 2 terms that are inspired by the MetaNet model. So this model, this term is actually literally copied from the MetaNet model. So we look at the downstream density, so density in the next, sorry, this is the upstream density, the density in the next segment. And if we see a difference here in the density, we multiply it with a certain parameter to affect our speed limit. And the same we can also do with the density of the next segment. And in this way, we can then relate the speed limit to the state of the system with some parameters theta, and they can then be optimized. An additional advantage is that we can take different parameters for every segment, but we can also say for the whole link, for every segment, we will just use the same parameters. And in that way, we get, again, a further reduction of the complexity. So that's for speed limits. We can also look at an on-ramp, and there we can use a kind of a proportional controller. So we look at the difference between the critical density and the current density, and that we parameterize and use it as an update of the current ramp metering rate. And actually, there's a very famous strategy for controlling freeways. It's called Alinea. It was also developed by Professor Papageorgiou, where the current ramp metering rate is updated with a value which is this occupancy. So this is related to how much or for how long a sensor detects a vehicle, but there is a relation between this occupancy and the density. So actually, these 2 relations are similar. The only difference is that in Alinea, the gain would be constant, whereas in parameterized MPC, we can actually update or re-optimize the gain regularly. So that is for highways. And we did a small case study. We used the A12 highway. And we looked here at the optimization of the total time spent and the total emissions. And here are some of the results. So we first consider the uncontrolled case. And there we have a total time spent of about 1,045 and 220 kilogram emissions. And of course, if you don't do control, you don't have any CPU time. If we then look at parameterized versus regular MPC, and we only look at optimizing the total time spent, then we see that with regular MPC, as expected, we can get a higher reduction of the total time spent. But you see that the difference between parameterized and regular MPC is relatively small, whereas we get a huge speed up in terms of CPU time. This also holds if you're going to optimize the emissions. So we can, in both cases, significantly reduce the emissions. And here, by coincidence, it's probably also due to model mismatches, actually the parameterized performs better than the regular MPC. But this is related to the fact that, for example, we did not take enough starting points for the regular MPC. In general, you would expect the regular MPC to perform better. And again, we see a speed up, and that also holds if we optimize a combination of total time spent and emissions. In all cases, we see that the performance between parameterized and regular MPC is similar, but we get a huge speed up. And that means that parameterized MPC is one of the ways to go if you need to control a huge traffic network.
Professor Schutter,
we can do something, yes?
For your parameterized MPC, do you fix the parameter for in the prediction horizon? So when you solve the MPC, you consider only one parameter. It's not time varying, or is it time varying?
If I recall well, in this particular problem, we fixed the parameters for the horizon. But in general, as I indicated in this figure, the parameter may also vary over the horizon. So you have actually a wide variety of choices. You can have the parameter change every time step. You can keep it constant for a few time steps, or you can keep it constant for the whole horizon.
Okay, thank you.
Okay. You can also do something similar for urban control, but in the interest of time, I will skip it because the situation is very, very similar. Another way to apply or to parameterize your control signal is in the special case that you have discrete controllers. So for example, an on-off controller or an open-closed actuator. Typical examples would be the opening of a shoulder lane. So an extra lane that you can open and close during rush hour. Or if you look at traffic signal control and you would only consider red and green as the main values, then you would typically have a discrete or a binary controller. And now you can approach this in two ways. Typically in the conventional MPC setting, you would for every time step define a level, a U, and then you would have in total n variables for a horizon of n steps, going from UK plus 1, up to the end value UK plus n minus 1. In general, then you get a mixed integer optimization problem. So mixed integer means that you have both real valued variables, like the queue lengths, which typically are approximated using real valued variables. And you also have integer optimization variables, namely the control inputs. Typically, mixed integer problems cause additional complexity, and they're also MP hard, which essentially means that the CPU time will increase exponentially, loosely speaking, with the number of variables. However, we can also look at this in a different way, and instead of looking at the values of the control signal, we can also focus on the changes. And that's then called time instant optimization. So we will, for example, say we are going to switch m times, so in our case, 2 times on and off, and we are now going to optimize the switching times. In that case, instead of having n binary variables, you will get m variables, and in general, or 2m variables, and especially if the horizon is large, that can again lead to a huge speed up of your problem because you have much less optimization variables. You go from n variables to 2n variables, to m variables where m is the number of switches. Okay. Now, if you look at a really huge system, then you will always run into problems if you want to control the system using a single centralized controller. And that's why for huge systems, the way to go is to subdivide your huge system into subsystems. And then we come into the field of distributed MPC. And what you see here is a representation of this. So we have our network, and we divide it in certain zones. So in our case, we have here a network consisting of 3 zones, a yellow zone, a blue zone, and a red zone. And for each of these zones, we develop a local MPC control agent. The idea is that now we don't have to take the whole network into account, but we can consider a smaller part of the network. And that means that we have a less complex model and also less control variables, and that may make the problem still tractable. And because typically the CPU time is an essential feature, and we have only a limited time to compute our control signals, so we have to make sure that we can compute the control signals in a good way, and so taking enough time to compute it within the allocated time slot. However, if we split the network in several parts, we still need some coordination between the actions of the control agents, because otherwise it could be that, for example, the blue agent has an issue in this node, there might be congestion, and the yellow agent might send actually a lot of traffic to that node. And that would then create an imbalance. So we also have to take care that the agents can kind of coordinate their actions. So they need to find local control inputs that will also contribute to the global optimum. And in this presentation, we will give a brief introduction on how this is done. And I guess that in later presentations today, people will go in more detail, and actually also in the presentations yesterday, on how to do this in various ways. So what we consider is that we have an agent, and we're going to look at the interactions between the agents, the interconnections. So the blue agent has some sort of an outflow. Let's consider here the interconnecting variables to be flows of vehicles. And that will then create an inflow to the region of the green agent and vice versa. So every agent has then a local model where some of the inputs are the local states, the local control inputs. We can also have disturbances. So in a traffic context, this would typically be the demand, so the number of vehicles entering the network. And then we have also variables that are generated by the neighboring agents. If we want to be more specific, we can even look at different inputs from different neighbors. So the J's are the neighbors of agent I, and each of these neighbors generates an inflow. And likewise, the agent will also create an outflow towards its neighbors. In general, if we would equalize the input and the output, we would again get an overall control problem that is centralized. If we would cut the connection between the agents, we get decentralized, localized problems, but then we get a mismatch between the inflow and the outflow. So we need to find a way to match the inflow and the outflow without creating one joint optimization problem. And this is done as follows. So we consider the optimization problems for the local agents, but we want to make sure that the input that agent I gets from agent J would match the output from J to I. And so in general, you want these equalities to hold, but you don't want to impose them directly in your optimization problem, because then you couple all the optimization problems and you create a centralized optimization problem. So what are we going to do? We can not use the values directly, but we will let the agents kind of negotiate and interact. And then we get the following setting. So every agent will solve a local problem, considering only its local control inputs and the local states, as well as the values it gets from the neighboring agents in their previous iteration. And in addition, we have an additional term that will actually take care of the matching between the inflows and the outflows. If we do it in that way, we have a decoupled problem, because the agent only has to optimize the inputs. But after every step of the optimization, we get a kind of a coordination between the agents that will also steer the interconnecting variables to similar values. Again, to be more in detail, typically what we would penalize is the difference between the previous value of the inflow and the actual outflow, and also the previous value of the actual outflow from agent I to J, and the inflow that is received from J to I. And the idea is that we then have two types of iterations. We have an iteration over k, but also an additional iteration within every optimization, where the agents at every time step solve their local problem and then exchange the values. So they would typically say to each other, okay, this is what I will generate as output towards you. And then the agent uses those values received as inputs and optimizes its own optimization problem, and then also communicates to the neighboring agents what are the output values. And then by including the difference between the input and the output and penalizing it, we will gradually see that these two values converge to each other. And in the end, we will then have a solution that will have these constraints satisfied and will also lead to local optimality. Okay. And that can be done in multiple ways. We have multiple iteration schemes. We have schemes based on Lagrangian multipliers, on auxiliary problems. This will typically be dealt in some of the other presentations. And I just want to show what would typically happen. So in the first iteration, we have here two agents. We have the outflow of agent 1 indicated in blue, the expected inflow of agent 2 in red, and we see that there's a mismatch. And then gradually, as the agents interact, we see that the two values will go closer and closer. And we also see that the difference between the outflow and the inflow will go from a value towards 0. So that's here indicated that we see that as the iterations and the interactions progress, that the values of the two agents will grow closer and closer. And at one moment, we decide that they're close enough, and then we can use the local control actions to apply to the local agents. And we are also sure that the interconnection, the interconnecting variables will be close enough so that one agent will not cause problems for the other agent. Okay. So there are many schemes, and this is actually a very active field of research. And if I was not mistaken, the ADMM method has been discussed in yesterday's presentations, but there are also methods based on games that will be discussed later today also by Professor Ming Chao, if I'm not mistaken. So this is a very active field of research on how to get convergence. Actually, it can be shown that in a convex setting, you will always get convergence. The disadvantage is that in traffic, we often have non-linear, non-convex settings, but we see that in practice, also for those cases, you can often get convergence, although proving it in a formal way is not always possible. So that's for distributed MPC. If we have a very big network, then one way to address the computational issues is to divide the network in subparts, and then for every subpart have its own local controller. But on the other hand, also make sure that the controllers interact and coordinate so that you get some global performance. However, if you have really a huge network, that might still not be sufficient. So if you have a large-scale network, I already indicated some of the issues, and you can do centralized control, but then you would typically run into computational issues. So one way to go is to go for distributed control. And in general, you then always have a trade-off between optimality and tractability. Typically, a centralized approach would be more optimal, but less computationally tractable, whereas a distributed control approach is typically less optimal, but more tractable. Advantages of centralized is that it will typically look better at global performance, whereas distribute looks more at local. On the other hand, a distributed control is more scalable. If you extend your network, then it's much easier to just add one local controller rather than to update the centralized control, because then the whole model of the whole network has to be updated. Also, a centralized controller is much more sensitive towards communication issues. And you need a big bandwidth to communicate or to transmit all the local sensor measurements to the centralized controller. And also in the centralized control case, if your centralized controller breaks down, then your whole network has broken down. In a distributed setting, if one of the controls breaks down, then some of the neighboring controllers may still partly manage to prevent huge congestion in the current network. And so that's an advantage of the distributed control approach. However, if the system is really huge, then even with the distributed control approach, you will in the end run into problems. And then it's useful to look at a multi-level approach. How does this work? So the idea is that just as in the conventional setting of distributed control, we still have divided our network in subnetworks. And for every subnetwork, we have a local control agent. But we will also consider a grouping of control agents, and several control agents will then be managed by a supervisor. So that's indicated here. So we get multiple levels of control with local control agents at the bottom level and then higher level agents at the higher levels, and also separation in time and space. And so the space-based separation is that we have divided our network using local control agents. They would typically take care of the local control and act in a quick time scale. For the supervisors, we typically consider larger regions, and they would also interact in a slower way. And then we get the following control hierarchy. So at the local level, we have control agents that take care of the fast dynamics in a small area. And that makes the problem still tractable. So we have a small area, but we also have a limited amount of time to compute our control signals. But this combination, small areas, fast dynamics, make the MPC problem tractable. The control agents, they would typically interact with each other. They would coordinate with each other to make sure that the local control actions will not create problems for the neighboring agents, and that you also get some degree of global optimality. However, it could be that sometimes the local control agents cannot reach an agreement. And in that case, there is a second control layer present, a supervisory control layer, that would typically interact over a larger area, but also at a slower rate. So typically you have slower dynamics, a larger area, and this combination also makes the MPC problem tractable. And so typically you would have more aggregate models, but you have more time to do the computations, and in the end, that would make MPC tractable. So that's then the setting. We have multiple control levels. At the bottom, fast dynamics, small areas. At the top, slower and slower dynamics, so less frequent interaction and larger areas. And these supervisors would then communicate with the control agents and make sure that in the case that the control agents cannot reach an agreement, they can indicate in which way an agreement should be reached that is then still, let's say, optimal or more optimal for the overall system. And of course, the supervisors would also interact, and it could be that in some settings you have a higher level supervisor to take care of the coordination of the supervisors. So this was already indicated. Lowest level, we typically do operational control, fast control, small regions, and for the higher levels, it's slower and larger, and you would typically look at more tactical and strategic control. And what is important that we get coordination not only within the levels, but also across the levels. And due to this combination of fast control and slow in small areas and slow control in larger areas, we can still apply MPC. Of course, there are a lot of issues that still remain. And so the question is, how can we define prediction models? Because in the different levels of the hierarchy, you would typically have different types of models. Also, how do we divide the network into subnetworks? What is the best possible division? Should this be done in a static way, or should we maybe change the boundaries of the regions in a dynamic way? How can we define the goals for the local control agents, for the supervisors, and so on, so that we can still reach a global goal? How to design the higher control levels, how to get interaction and coordination. And also, how can we extend this if we look at more complex models? If we also, for example, take on-off control into account, if we look at different modalities of our traffic network, it could be that we have a congested mode, an uncongested mode. And the main issue is, of course, how to reduce the computation time. And this is still a very active field of research, not only for traffic networks, but for networks in general. And both theoretical research has been done or is being done, as well as more applied research. And in the next slides, we will answer some of these questions for the case of traffic networks. And there we will consider the following hierarchy. So at the local level, we would typically look at, for example, individual ramp meter controllers or individual dynamic speed limit controllers, or in an urban context at specific intersections and the local traffic signal controller. In a highway, we would then coordinate several ramp meters and several speed limits for a stretch controller. So one highway consisting of several links, several segments. For each segment, we might have a different ramp meter controller if there's an on-ramp, or we might have different speed limit controllers, and they are, of course, interacting locally, but they are coordinated by a stretch controller. Likewise, if you look at an urban context, there might be a ring road or a corridor, and you can coordinate the individual traffic signal controllers for the individual intersections using a corridor controller. Several stretch controllers or corridor controllers in an area can then be controlled by an area. That's, for example, a city or a part of a city, and then we can go to the city level or the region level or even the provincial level. So there are many hierarchy, let's say there is a hierarchy depending on the scope, both in space and time of the controllers. How would then the controllers look like? Typically for the lowest level controllers, especially traffic signal controllers, which have to be updated every second, or ramp metering controllers, which also have a high update rate, we would look at very basic controllers like PID controllers, logic-based controllers, fuzzy controllers, rule-based controllers, heuristic controllers. If we then go up in the hierarchy and look, for example, at the coordination of several dynamic speed limits or the coordination of several intersections, then we can start to use MPC. MPC at the corridor and the level and the freeway stretch level would typically take care of coordination and provide set points for the lower level controllers. For example, a ramp metering rate or a green fraction for the traffic signals. If you look higher into the hierarchy, you will look more and more towards the network level. And then not only the coordination of controllers takes an important role, but also how you're going to route the traffic flows through your network. So for the area controllers, it would typically be to assign traffic flows to different highways. And for the regional controllers, you're going to look at a higher level. You might consider a city that is divided in certain areas, and you want to kind of route the traffic from one area to the other, but not at the road level or at the freeway level, but considering even different areas. Since we typically now get, due to this temporal and spatial division, medium-sized problems, we can still get a tractable control approach. And later in the next slides, I will focus on the regional controllers. Okay. So the regional controllers would typically kind of interact or coordinate a collection of areas. And the idea is that the regional controller would determine for every area, and we are typically looking now at an urban context, what is the optimal flow of vehicles from one area to the other. And for this, we are going to use the so-called macroscopic fundamental diagram. It's an extension of the fundamental diagram from an individual road to an entire area. And we will see that originally we get a nonlinear, non-convex optimization problem, but we will be able to transform it into a mixed integer linear programming problem. So what is the macroscopic fundamental diagram? It was introduced by Geroliminis and D'Aganzo, And it would typically describe the relation between the average density in an area, so vehicles per kilometer, and the outflow or the flow in the region. And you get a curve that is very similar to the critical diagram that I'd shown earlier for a freeway. So typically, if the density is low, you get a free flow regime. You reach a critical density, and then you typically get a breakdown. Earlier on in the slide, this was for one particular freeway, but this similar type of behavior can often be seen in city areas up to 10 square kilometers. And this is an important, let's say, relation that we can then use to describe the behavior of entire areas. And there's also a law that says that the outflow of the area is proportional to the flow within the area. And that's actually a law that we are going to use. So we are going to present our whole network by a graph where links correspond to areas. So areas have a certain inflow and a certain outflow and also a density. And then if two areas connect, that's represented by a node. In addition, we also have external inflows and external outflows, and they are described also with nodes, so external origins and external exits. And then we have, of course, the network macroscopic fundamental diagram that would relate the density inside an area with the outflow. So that's the first law that we're going to use. Then we have a conservation law, once we have also seen before, stating that the inflow minus the outflow will provide an update of the density. And finally, we also have a balance of inflows and outflows at every node. So the outflows, both the external outflows and the ones towards the neighboring areas, equals the inflows from the neighboring areas, and also, this is the inflow. So that's the inflow in the current area, which is the outflow of the neighbors, and of course the external inflow, and that equals then the outflow towards the neighbors. So the outflow of the current agent will be the inflow of the neighbor and also the exit flows. And we need a balance between all of them. Okay. Then we want to keep the density in each region below a critical density. So that's also related to the question that was asked earlier on regarding the Lyapunov approach, but we do it in a way that we only penalize when we are above the critical density. If you are below the critical density, we only impose a zero penalty. And in addition, we also want to minimize the total time spent by all the vehicles in the network. And that total time spent is equal to the number of vehicles in the network multiplied by the length of the local network multiplied by the time step. And in general, you would take a weighted combination between preventing, let's say, congestion, and minimizing the total time spent. So this gives the following total objective function. Now, in general, you can also impose additional constraints, such as maximum flows from one area to the other. And in general, if you look at the problem, we get a nonlinear non-convex optimization problem, where the max causes one of the non-convexities, nonlinearities, and a macroscopic fundamental diagram is also causing a nonlinearity. So how do we now deal with this? So we want to now transform this into a mixed integer linear programming problem. And for this, we use the following equivalences. So there's an equivalence that states that if I have a Boolean statement, for example, stating that a certain function is less or equal than 0, that this can be related to a binary variable being 1, if we consider the following equivalent statement, where capital M is the maximum of the function, small m is the minimum of the function, and epsilon is just a small numerical tolerance to translate a strict inequality, so f bigger than 0 will be translated to f larger or equal than epsilon. And it can be shown just by filling out delta is 0 and delta is 1, that these two statements, that they are equivalent to this Boolean equivalence. And it's important to note that if f is an affine function, this is actually an affine expression, so a linear expression. Likewise, if you have the multiplication of a binary variable and an affine function, which is in essence a nonlinear relation, that you can rewrite it in 4 conditions by introducing an auxiliary variable y, where capital M is again the maximum of f, m is the minimum of f, and in the case f is linear, we see here actually 4 linear inequalities. So that's actually the main message. We can translate a Boolean statement and a nonlinear multiplication into linear equations. Of course, the equations would involve binary variables, so we typically get mixed integer linear programming. So now if we have this nonlinear function that we had initially, then we can approximate it in a piecewise affine way. So we are going to divide the whole density range into a certain number of regions, and in every region we approximate the nonlinear function in a linear way. So we get a piecewise affine function. And that means that we can approximate the nonlinear function in this way. So we get a linear expression if the density belongs in a certain region. And then we can actually use the statement that we had before. So if the density is less than a certain variable value, we let that transform to delta being equal to 1. That we can transform into mixed integer linear programming equations using the first equivalence. And if we do this, then we can actually capture the whole nonlinear or the whole piecewise affine function by making use of the binary variables into one global linear expression. Because in every region, one extra delta value will become equal to 1. And then we can just, by considering the difference between the coefficients, gradually build up the whole piecewise affine function. Of course, if we do this, then if we work out the equations a bit more, we will get multiplications between the row and the binary variable delta. But such a multiplication we can also transform into MLP equations using the second equivalence. So then we get linear relations, but we also have to deal with the objective function. The total time spent was already a linear term, but our objective function is still nonlinear because we have the maximum of 0 and a linear term. However, since this is a convex piecewise affine function, so a convex objective function, we can introduce a dummy variable and state that the new variable theta should be larger than 0 and also be larger than this term. And if we then minimize theta, then it can be shown that in the optimum, theta will be equal to the maximum. And if we then combine everything, we see that we have linear state equations, we have linear constraints, and in the end, our objective function is fully linear. And that means that we can solve the optimization problem using mixed integer linear programming. And then you can proceed in 2 ways. You can either apply it directly, or you can solve the MLP problem and then use it to solve the original nonlinear optimization problem. And the same thing can also actually be done for other problems. I don't have the case study in this slide, but I will show a case study in an additional set of slides. So I'll quickly go to the additional set of slides to just illustrate how it would work. So we do it for area controllers, but the outcome is still the same. So we get that our original problem is nonlinear, but our approximate problem is a mixed integer linear programming problem. And I will show a small case study with 3 nodes and interconnecting links. And the main message is the following. So again, we can do no control. We can look at the mixed integer linear programming solution. We can look at the nonlinear optimization with a limited number of starting points and more starting points, or we can use one run of MLP and use that solution as an initial point for the nonlinear optimization. So you see that if you consider the nonlinear control compared to the nonlinear, that of course the nonlinear will be better. In general, nonlinear will be better if we consider more points, more starting points, and it will in general also be better than the MLP. However, if we combine the MLP with the nonlinear optimization, so then we actually start from a good initial point, then we see that in this particular case, we are actually approximating or being equal to the performance of nonlinear optimization with a lot of starting points, but we can do it much faster. We see that we only need 1.3 seconds for this approach compared to 900 seconds if we really optimize 50 different initial starting points. And that's actually one way to use or to speed up the optimization. We can either directly use the MLP solution, or if you want even increased performance, we can do the nonlinear optimization using the MLP solution as a starting point. And that's again an illustration of like kind of approximating your original MPC problem by a simpler problem, and then either using the solution directly or using it in subsequent optimization. So now we go back to the main presentation. And the work that I've presented today, of course, does not only apply to conventional traffic control, but also to traffic control systems that are multimodal, so that include rail networks, public transportation, and so on, and also for transportation systems that include intelligent vehicles. That will actually be a topic that will also be considered in the presentation of Professor Papageorgiou. He will look at autonomous vehicles and vehicles that interact with each other. But the whole idea, so the different approaches that I have discussed today, they can also be applied in that type of networks. Actually, and that's something that you will probably also see in other presentations in this summer school, the networks that we considered, they can actually be more general. And because typically what we have is we have a network where something, a commodity, is moving on a network. The commodity in this presentation today were cars, but they could also be electrons or water molecules or trains or packages. So that means that the networks that have been considered today, they would also be generalizable, and the approaches for MPC, parameterized MPC, distributed MPC, multi-level MPC, they can also be applied to smart grids, to water networks, railway networks, and logistic networks, because at some high level of aggregation, we can describe all these networks using similar dynamics. Of course, you still have application-dependent, let's say, knowledge and information that you should include, but the main message is that similar strategies can also be applied here. So to conclude, I have given an overview of some of the work that has been done in the literature, as well as by my own team, in the field of model-based predictive control for large-scale traffic networks, considering both urban and freeway networks. And the main issue was the computational complexity. And there you had a trade-off between accuracy and efficiency. If you want to be very accurate, you typically need a huge CPU time. If you want to be faster, you would typically have to trade in some accuracy. And some of the solutions that we have discussed was the use of macroscopic models, Also to parameterize your controller, to approximate your original problem by a simpler problem, and for really large-scale networks to either go for distributed control or for multi-agent control. And actually, a lot of our ongoing work is to keep on extending these approaches. And in a recent work, that's an ERC project that was recently approved, we are going to look at how we can combine optimization-based control with learning-based control to further explore this trade-off between accuracy and efficiency, where the optimization-based approaches would typically yield optimality, and the learning-based approaches would typically yield online speed. And if you want to have more information on the work that was presented here, you can also look at my website. The publications are listed here. So I'd like to thank you once more for your attention and open the floor for questions.
Thank you, Professor Bart de Schutter. It's a really nice talk. It links all the patents that we have in the summer school. Then for the audience, if you have questions, please unmute your microphone and speak out directly. Akilas.
Hello, can you hear me?
Yes.
Thank you for the very interesting presentation. My question is, for example, in the parameterized MPC that we saw earlier in the slides.
Yeah, I will go back to the slide maybe to explain.
My question would be here, okay, so we do, let's say, parametric approximation of the solution and the policy.
Yes.
Is it possible that we will get results that are not feasible?
Yeah, so that's a good question. So suppose that we are looking at, for example, the ramp metering situation. Yeah. So a ramp metering rate would typically be between 0 and 1, 0 blocking all traffic, 1 emitting all traffic. So this is a kind of a simplification. Normally, you would have to add a saturation here. So you would have to impose that this rate, if it's bigger than 1, you cut it off. And if it becomes negative, you also cut it off. So that's how you can deal with feasibilities at the input level. Of course, if you have a parameterized control law, you might still get infeasibilities at the state level. Yeah? But typically, we would take care of that by including the constraints in our optimization when we do the MPC, the optimization of the parameters. Of course, since in reality, there might be a mismatch between the model and the system, you could, when you're actually going to apply the control law to the system, you might have a constraint violation, but the same thing might actually also happen with regular MPC due to the model system mismatch. One way to deal with this is to, for example, make your constraints a bit tighter than what you actually need. And also take into account that a lot of constraints in a traffic context are not really that hard. For example, like queue lengths, if there's 1 vehicle extra in the queue, that would typically not have a huge impact. Does that answer your question?
Yes, thank you very much.
Okay. So we have plenty of time for other questions. Okay, maybe for the organizers, if there are additional questions later on, maybe the questions could be forwarded by email to me, then I can reply by email.
Yes, if audience states, oh, there is a question from
Okay. Yeah.
Hello, my name is Sophie, and I have a question regarding your multi-level MPC approach.
Yes, I will maybe first show the slide then.
Yeah, I think you slightly mentioned that at some point, but I was wondering if you analyzed at all like the stability of the interacting MPCs. And I mean, I assume that it's quite difficult if you have different, from what I understood, you have different time scales.
Yeah. Yeah.
and you have the low-level PID controls and then 4 levels of MPC on top. Like,
yeah.
What is your experience, at least like experimentally, from like the stability point of view?
Yeah, so that's a good question. The answer is actually twofold. So if we look at this in a theoretical context, in the case that we have, for example, linear systems, then we can indeed do stability analysis in a formal way. If we go to traffic networks, and especially if we have multiple levels, then the analysis becomes much more difficult. And then there are two aspects. The first of all, of course, is how do you define stability? Stability in the conventional systems theory context is typically defined as a state going to zero. In this type of models, typically we would define stability in a somewhat different way. One way could be that you want your queue lengths to stay bounded. And that would then be a different way of defining stability. That would be more kind of practically relevant, rather than saying, for example, that all your queue lengths or all your number of vehicles go to zero, because then you would have essentially an empty network. And so from that point of view, we have seen in our networks, in our simulations, that of course, formally speaking, since the number of vehicles that enter a network is finite, by definition, you always have some measure of stability. But that's, of course, not a very satisfactory measure of stability. So what we typically see in our simulations is that if you would just optimize, for example, total time spent, you might indeed get that some queue lengths will keep on growing and growing and growing. So from a practical point of view, we would typically also penalize queue lengths just to make sure that we don't get the undesired behavior. But the theoretical analysis is extremely hard, both because of the nonlinearity and the fact that you would not study stability in the formal way. In the formal way is defined in conventional systems theory. Okay. Would that answer your question?
Yes, thank you.
Okay. So if there are any other questions, so please feel free to go ahead to unmute your microphone and ask your question.